Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky. Lord of the Rings. Exploring the wonders of Saturn. The planet Saturn has captivated human curiosity since ancient times. Known for its striking appearance and distinctive features, it was first observed by early astronomers, with records dating back to antiquity, including mentions in Babylonian texts and by ancient Greek astronomers like Ptolemy. However, it wasn't until the invention of the telescope that Saturn's true nature began to be unraveled. In 1610, Galileo Galilei turned his telescope towards Saturn and made a puzzling discovery: what appeared to be large, protruding ears on either side of the planet. This observation led to centuries of speculation and debate about the nature of Saturn's unusual appendages. It wasn't until the 1650s that Dutch astronomer Christian Huygens correctly identified these features as a flat, ring-like structure surrounding the planet. Saturn's rings, composed primarily of ice and dust particles ranging in size from micrometers to several meters, are one of its most iconic and recognizable features. They are divided into several distinct rings, labeled alphabetically based on their order of discovery. The main rings are the A, B, and C rings, with the Cassini division separating the A and B rings. Numerous smaller ringlets and gaps also exist within Saturn's ring system, adding to its complexity and beauty. The study of Saturn has played a crucial role in advancing our understanding of planetary science and astronomy. Spacecraft missions like NASA's Voyager and Cassini-Huygens have provided unprecedented insights into Saturn's atmosphere, rings, moons, and magnetic environment. These missions have expanded our knowledge of planetary dynamics, magnetospheric processes, and the formation of planetary systems. Saturn is the sixth planet from the Sun and the second largest in the solar system, boasting a diameter of approximately 116,460 kilometers at its equator. Its mass is around 95 times that of Earth, yet its density is remarkably low, indicating a composition primarily of hydrogen and helium, similar to Jupiter. The planet's atmosphere is characterized by swirling bands of clouds, primarily composed of ammonia crystals and other compounds. Saturn's prominent feature is its hexagonal-shaped polar jet stream, a mysterious and unique phenomenon observed at its north pole. Saturn's rings are an intricate system of icy particles, ranging from fine dust to larger boulder-sized chunks. These rings span an impressive distance of tens of thousands of kilometers but are remarkably thin, with a thickness of just a few meters. They reflect sunlight, creating a dazzling spectacle when viewed from Earth or spacecraft. Saturn's rings are a captivating and dynamic feature that has fascinated astronomers and the public alike. These rings are believed to have formed from the debris of a shattered moon, comet, or icy body that was torn apart by Saturn's gravitational forces and tidal interactions. The rings are primarily composed of water ice, along with traces of rocky material and organic compounds. They exhibit complex structures, including gaps, divisions, and braided ringlets, influenced by the gravitational interactions with Saturn's moons and the planet's own rotation. Saturn's main rings are categorized into several major divisions. A ring, the outermost and brightest of Saturn's rings, primarily composed of ice particles. B ring, located inward from the A ring. The B ring is broader and contains a higher density of material, including larger particles. C ring, the innermost visible ring, located just outside Saturn's upper atmosphere. It is less dense than the A and B rings and contains finer particles. Additionally, the Cassini division separates the A and B rings, appearing as a dark gap due to reduced particle density. Other divisions and gaps within Saturn's ring system, such as the Encke Gap and Keeler Gap, are named after astronomers who made significant contributions to the study of Saturn's rings. Recent observations and studies have revealed the dynamic nature of Saturn's rings, with processes like ring shepherding by moons and the formation of transient features providing insights into their evolution and stability over time. Ongoing research and future missions aim to unravel further mysteries surrounding Saturn's rings and their role in planetary formation and dynamics. Saturn boasts a remarkable moon system, with over 80 confirmed moons and countless smaller moonlets orbiting the planet. These moons vary greatly in size, composition, and characteristics, offering a diverse range of environments for scientific exploration. Some of the main Saturn's moons include Titan. Titan is Saturn's largest moon and the second largest moon in the solar system. It is unique among moons in that it has a dense atmosphere primarily composed of nitrogen, with traces of methane and ethane. Titan's surface is shrouded in a thick haze, making direct observation challenging. However, spacecraft missions like Cassini-Huygens have provided detailed maps of Titan's surface, revealing lakes, rivers, and dunes made of organic compounds. Titan's atmosphere and surface features make it a fascinating target for studying prebiotic chemistry and potential habitability. Enceladus. Enceladus is a small moon but of significant interest due to its geologically active nature. It has a global subsurface ocean beneath its icy crust, with geysers erupting from fractures near its south pole. These geysers eject water vapor, ice particles, and organic molecules into space, creating a plume that has been sampled by spacecraft like Cassini. Enceladus's subsurface ocean and potential for hydrothermal activity make it a prime candidate for studying astrobiology and the search for life beyond Earth. Rhea. Rhea is Saturn's second largest moon and is primarily composed of water ice. It has a heavily cratered surface, indicating a lack of geological activity compared to moons like Enceladus. Rhea's surface features, including valleys and impact craters, provide valuable insights into the Moon's geological history and the dynamics of Saturn's moon system. Mimas. Mimas is known for its distinctive crater named Herschel, which gives it a resemblance to the Death Star from Star Wars. The impact that created the Herschel crater nearly destroyed Mimas, highlighting the violent history of impacts in the Saturnian system. Dione, Tethys, and Iapetus. These moons also exhibit unique characteristics, such as Dion's wispy terrain, Tethys's prominent impact basin Odysseus, and Iapetus's stark contrast between its bright and dark hemispheres. Saturn possesses a complex and dynamic magnetic field, generated by convective motion within its metallic hydrogen interior. This magnetic field extends far beyond the planet, forming a magnetosphere that interacts with solar wind particles and cosmic rays. Saturn's magnetosphere is asymmetric, with a magnetotail extending in the direction opposite to the solar wind. This magnetotail can extend over millions of kilometers and is influenced by the planet's rotation and its moon's interactions. It contains radiation belts similar to Earth's Van Allen belts, consisting of charged particles trapped by the magnetic field. These radiation belts pose challenges for spacecraft operations and exploration near Saturn. Saturn's magnetic field also contributes to the generation of auroras near its poles. These auroras, known as Saturnian auroras, are visible in ultraviolet and infrared wavelengths and provide insights into magnetospheric processes and particle interactions. Saturn's atmosphere is a dynamic and complex system characterized by distinct cloud bands, storms, and atmospheric phenomena. Cloud bands. Saturn's atmosphere exhibits alternating light and dark bands caused by differences in cloud composition and altitude. These bands are primarily composed of ammonia ice crystals, with darker regions likely containing organic compounds and other complex molecules. Hexagonal storm. At Saturn's North Pole, a persistent hexagonal-shaped storm has been observed in the upper atmosphere. This unique feature, first discovered by the Voyager spacecraft, is a striking example of atmospheric dynamics and fluid mechanics on a gas giant planet. Great White Spot. Periodically, Saturn experiences a phenomenon known as the Great White Spot, a massive storm system that can encircle the planet and last for several months. These storms are thought to be driven by seasonal changes and atmospheric dynamics. Studying Saturn's atmospheric dynamics provides valuable insights into weather patterns, atmospheric circulation, and the behavior of gas giants in the solar system. Advanced spacecraft missions like Cassini have revolutionized our understanding of Saturn's atmosphere, revealing its complexity and variability over time. Saturn's interior structure is a subject of ongoing scientific inquiry, with models based on data from spacecraft observations and theoretical simulations. Core formation. It is believed that Saturn has a rocky core at its center, composed of heavy elements like silicates and metals. This core likely formed early in the solar system's history through the accretion of solid materials. Layered structure. Surrounding the core, Saturn has a mantle layer consisting of liquid metallic hydrogen. Under extreme pressure and temperature conditions, hydrogen transitions from a gas to a metallic state, creating a conductive layer that generates Saturn's magnetic field. Outer atmosphere. Above the metallic hydrogen layer is Saturn's outer atmosphere, composed mainly of hydrogen and helium gas. This atmosphere extends outward into space and is characterized by cloud layers, atmospheric dynamics, and weather systems. Understanding Saturn's interior structure provides insights into its formation and evolution as a gas giant planet. Models incorporating data from spacecraft missions like Cassini-Huygens and theoretical simulations help refine our knowledge of Saturn's internal processes and composition. Saturn plays a significant role in the dynamics and evolution of the solar system, influencing planetary orbits, gravitational interactions, and the formation of celestial bodies. Orbital dynamics. Saturn's gravitational influence affects the orbits of nearby planets and asteroids, contributing to orbital resonances and stability within the solar system. Its interactions with Jupiter, in particular, have profound effects on the distribution of small bodies like comets and asteroids. Ring dynamics. Saturn's ring system provides valuable insights into planetary formation and dynamics. Studying the origin, evolution, and stability of Saturn's rings helps scientists understand the processes that shape planetary systems and their debris disks. Magnetospheric interactions. Saturn's magnetosphere interacts with solar wind particles, cosmic rays, and charged particles from its moons, shaping the environment around the planet and influencing space weather phenomena. By studying Saturn's role in the solar system, scientists gain a deeper understanding of planetary formation, dynamics, and the broader context of planetary systems within the galaxy. Current research on Saturn focuses on several key areas, including moon's inhabitability, continued exploration of Saturn's moons, such as Titan and Enceladus, aims to assess their potential for habitability and the presence of organic compounds essential for life. Atmospheric studies. Advanced telescopic observations and spacecraft missions study Saturn's atmospheric dynamics, weather patterns, and long-term climate changes. Ring dynamics. Research into the formation, evolution, and stability of Saturn's rings provides insights into planetary ring systems and their role in planetary formation processes. NASA's upcoming Dragonfly mission, planned to be launched in July 2028, aims to explore Titan's surface using a rotorcraft to study its geology, chemistry, and potential for prebiotic chemistry. In conclusion, Saturn stands as a fascinating celestial body that continues to intrigue and inspire scientific exploration. From its mesmerizing rings and diverse moon system to its complex atmospheric and magnetospheric dynamics, Saturn offers a wealth of knowledge about planetary formation, evolution, and the broader context of the solar system. Ongoing research, spacecraft missions, and technological advancements promise to unveil further mysteries of Saturn and deepen our understanding of planetary systems, habitability, and the search for life beyond Earth. As humanity continues to explore the cosmos, Saturn remains a symbol of discovery and wonder, inviting us to unlock its secrets and unravel the mysteries of our cosmic neighborhood.